Hi, I'm Conor Houghton, and this is Information Theory Lecture 1, part of Information Processing and the Brain, a unit we give at Bristol University. Uh, this lecture is about motivating information theory. It won't contain much detailed information about information theory, and in fact, the course doesn't go in depth into information theory. It's mostly supposed to give you some basics and some feeling for what information theory does. Information theory is a theory of communication. That's the headline. To start with, to motivate why we would teach information theory as part of a course called Information Processing in the Brain, well, the answer there is twofold and contradictory. On the one hand, clearly, information theory is likely to be important when considering the brain. The brain is is an organ for processing information, and indeed, information theory quantities have proved useful in analyzing neural data. Information theory based objective functions have proved useful in things like deep learning, and we believe there to be some relationship between how machines learn in modern machine learning and artificial intelligence is, and how the brain works. That's the one hand. On the other hand, as I said, information theory, as originally conceived, is a theory of information. Information is generated by a source, sent along a channel, and received by a receiver. When talking about the brain, it isn't so clear what the source is, who the receiver is, what the channel is. And often when we use information theory as applied to the brain, we're a bit vague about that. Also, of course, the brain is an organ for extracting salient information from information. All this stuff comes into our eyes, our ears, from our memory, and we choose the bits that are important that we can use for inference. Information theory isn't a theory of salience, although a theory of salience possibly will be built out of information theory. There are ideas like information bottleneck, rate distortion theory that head in that direction. So, on the one hand, information theory is useful for the brain. It's useful for data analysis in the brain. It's useful in machine learning, which might tell us something about the brain. On the other hand, the brain is a challenge to information theory, and it's possible that by thinking about the brain and about information theory, we'll be able to come up with new extensions to information theory that will be useful. So, the theory of information is a theory of communication. You have a source, you have a channel, you have a receiver. You imagine a person with a radio broadcaster, you imagine radio waves, and you imagine somebody with a radio tuning in, hearing some wavering sound and asking, how much information can I get from these sounds I get from my radio? And so the information theory is the mathematics that the receiver might use to quantify the amount of information that's potentially available in the communication channel that they are using. There are information theory quantities which might tell the receiver how much information about the source is available in that channel. But for now, we just look to answer the question, can the receiver decide how informative the channel is likely to be, how much information there is in the channel? So we have to start off by thinking a bit about randomness. The key here is that if the information in the channel is predictable, the receiver is not going to learn very much from it. And so what we have to start doing is to start to think about probability as a measure of ignorance rather than randomness. When we first start learning probability theory, we think about truly random things, flipping coins, Geiger counters, etc., things that we have no that are truly random. I mean, flipping a coin isn't truly random, but as far as we're concerned, without doing the incredibly precise measurements of the thumb movement that we require to predict the outcome, flipping a coin is truly random. The emission of alpha particles from a radioactive source really is random. It's quantum mechanically random. But what we want to do instead is to think about probability distributions as measuring not randomness, but unexpectedness. So that's the theme of this lecture, about the relationship between randomness, unexpectedness, and information theory. And again, in doing that, we're considering information theory as a theory of communication. So let's think of an example. So Netflix is always a good example, mostly an example people use because of the Netflix Prize dataset, which I'll discuss shortly. But here's a simple version of the story. You watch a film, you make some star ratings on the film. Netflix probably uses other information like what other films you've watched, etc. But by you star rating the film, and I'm not sure anybody actually does star rate films anymore, but let's imagine that when we watch films, we give them between 1 and 5 stars. And then Netflix can use that to decide how good films are. They can also learn more about you and decide what sort of films you like based on which films you give high star ratings to. And if somebody else is watching, they can decide if that other person, based on their ratings, is similar to you, and they can use that to recommend films to you. So here are the films that Netflix is recommending to me at the moment. So if I go into my Netflix and I look for the films it has queued up as films it thinks I'd like to watch, that's a channel of communication. There's the films, there's Netflix, there's me. The films have some intrinsic quality or worth. In between, there's the Netflix recommendation engine, and then there's me. And so what the recommendations are doing is it's communicating to me something about the films. The films have some quality. I want to learn about that quality. I'm doing that through the Netflix recommendation engine. And we might ask, just how informative is that? Well, these are the films that it recommends to me. American Beauty, I did actually see that when it came out. I quite liked it at the time. These days, I think if I watched it again, I'd find it problematic in all sorts of ways. Not sure I'd enjoy it. Uncut Gems, I mean, why is it bothering telling me that? Everybody knows Uncut Gems is a good film. There's a lot of buzz about it. The Imitation Game, maybe that's a good film. I regard Benedict Cumberbatch as unwatchable. He's like a toff, and he gets to play my hero, Alan Turing. I would, prefer to gouge out my eyes with a spoon than watch The Imitation Game. He was quite good in Patrick Melrose, otherwise unwatchable. So I'm not sure exactly how much I've learned from the Netflix recommends engine. Some of it, well, my attitude to Benedict Cumberbatch, there's no way I could really have predicted that. Uncut Gems, it hasn't really communicated anything to me very effectively there because, as I said, everybody knows Uncut Gems is a great film. So we have an attempt to communicate. We have a communication channel from the worth of films to me via the Netflix recommendation engine. This is what's produced. How much am I learning? How much information am I likely to learn about the quality of films by looking at my film recommendations? We're going to look or discuss a simplified version of that, but this is the paradigmical example I want to use in discussing information theory. As I said, one reason people often use Netflix film recommendations as an example is there was, at the very dawn of the modern machine learning, artificial intelligence era, a prize, the Netflix prize. The Netflix released an anonymized data set which contained users identified by IDs, films actually identified by their names, and the dates that these anonymous users watched the film. That actually causes problems because it turned out to be possible to partly de-anonymize the data set based on people's recommendations on other recommendation sites that coincided with their recommendations on Netflix. But either way, the point was that they gave out this data set. You can still download it. I got it from Kaggle recently. And the challenge was to produce, there was obviously withheld information, the same people that they'd given you a rating information for, the information about what films these people had liked. They had other films that they'd watched and the ratings they gave them. You were supposed to predict that, and you were supposed to beat by 10% the best pre-existing algorithm, which was called Cinemax. And there was a £1 million prize for winning. And basically what happened was the various teams that were doing well teamed up together. Some of those teams were teams that then went on to become leading people, or members of those teams became leading people in the deep learning revolution. Actually, were already famous AI folk, but they teamed together and they did in the end win this prize. This graph here shows all the entries. You can see that to get the wooden spoon, you had to be quite talented, because just predicting that somebody would always rate a film as 1 star would be better than what you needed to do to get the wooden spoon. But you can see, surprisingly, that rating films as 4 is already pretty good. You can see the 0 line there with Cinemax, but you're already kind of a long way towards it by always predicting something has 4 stars. And that's, of course, pretty crappy. I mean, although in some ways it's a reasonably good predictor, or at least there are entries, as you can see, to the left of the 4 line that did worse. So these people made some effort to use an algorithm. They did worse than just always getting 4. But if you just told everybody that all the films they wanted to watch were basically 4-star films, then what you're telling them, although it has some sort of accuracy, is not useful information to tell them. And that's kind of the idea that we're trying to get at. So, the Netflix prize, the way you did it, you had to work out something about the person watching the film as well as the film itself. But just as a quick example, let's just consider the star ratings of films themselves. So based on the Kaggle data, I took a quarter of the data basically, because it comes in 4 chunks. I looked at all the movies and I averaged for each movie I got an average star rating by averaging across all the participants who rated it, and then I worked out how many movies got 1 star, 2 star, 3 star, and 4 star. I've rounded down here, so this is very crude, and it's only supposed to be an example. You should download the Netflix data and play with it yourself if you want to do anything more interesting. But what I saw was that basically almost 6% of people, or around 5.7% of people, rated movies. 0.057 of movies had an average rating of between 4 and 5 stars, and then 0.627 of movies had a rating between 3 and 4 stars, etc. So these things aren't meaningless. On the same data set, I looked to see what the least well rated film was and the most rated film. So Hedwig and the Angry Inch was the film with the highest average number of stars. Avia Vampire Hunter was the one with the lowest average star rating. And that's not terrible. Hedwig and the Angry Inch is a pretty good film. When it came out, there was a lot of buzz about it. I went to it. I really enjoyed it. Lots of people I knew went to it. We talked about it. It was very, very interesting and exciting to watch. Avia Vampire Hunter, I never heard of. I looked it up on the internet. Apparently it was really terrible. So the star rating is telling us something about films that is related to how good the films are. But the thing to notice is that, if this was a communication channel, you wanted to know something about a film, and what you looked at was what the average number of stars it had rounded down. So I pick a movie at random from the list of however many movies it was that have star ratings in these data, and I look to see how many stars it is, and that's supposed to tell me if it's a good film. And sometimes the film will have 4 stars, and that pretty much means it's a pretty good film. I looked at the other films, so the next one I saw was The Night of the Hunter, which is a great film, etc., etc. So sometimes when I look at this star rating, I learn something very important about the film. It's a 4-star film. That's very rare. And so when something is a 4-star film, it's probably very good. Even rarer are 1-star films. So again, I pick a film at random. I look to see what its average star rating is, and it's 1 star, and it must be really terrible because very few films have 1 star. But the problem is that most of the time I learn that the film has 3 stars or 2 stars. Almost 2/3 of the time I learned it has 3 stars. 1/3 of the time I learned it has 2 stars. And so typically what I learn about the film from looking at this star rating is that it's a reasonably good film. It's part of one of the best 2/3 films that you're likely to see according to the star rating. And so although sometimes the star rating allows me to learn something important and rare, that it's a 1-star film and therefore terrible, or a 4-star film and therefore likely to be excellent, most of the time what I learn from looking at the star rating is that it's a 3-star film, in which case it's probably okay. And that's not very informative most of the time. And in that way, this star rating is a poor communication channel. So the source here is obviously films. We want to know about films. So that's you. You want to know if a film is good. And in between, you're being told the average number of stars that people who've watched that film have given it. And if you do that, most of the time you learn something reasonably uninteresting. So you more or less will expect, certainly, that almost every film you look at will have 2 or 3 stars, and you'll have a pretty good idea that the film that you look at in this way, that whose star rating you will look at in order to assess the film, will have 3 stars. And so the star rating that is given to the film is not as unexpected as it could be, and therefore the act of looking at that star rating is not as informative as it might have been. And a way of thinking about that is, to you, it's not as random as you would wish it to be, in order to learn as much as possible from this communication channel. So the important thing is the star rating isn't random. It's not random in the way that a Geiger counter is random. The film already has a star rating before you look. It's a bit random in that there are quirks of people's attitude to films, the politics or the zeitgeist of the time when the film was watched, what else was happening, that might affect the star rating. As I said, Hedwig and the Angry Inch was a very good film. I don't think it's as good as Night of the Hunter. It was a much more recent film, and a lot of people were talking about it because it was, controversial at the time, although hopefully these days it wouldn't be so controversial. And so there's some random element that goes beyond the intrinsic quality of the film at play there in the ranking, the star ranking the film gets. And so there is some noise, but that noise isn't what we're talking about when we ask about the unexpectedness of the star rating. The unexpectedness, which here is not as large as it could be for this to be a good communication channel. Here's another example I always like to tell. It's the fable of Stefan. So not in this university, but in my previous university, I had a colleague called Stefan, and he was very boring, and he would always say the same things. And at the time, it was during the Irish boom, and we kind of all knew that the boom in the Irish economy was going to end, and there'd be a terrible crash. None of us quite expected that it'd be as terrible as it was going to be, or we wouldn't have bought houses. But Stefan, who was generally a gloomy chap, anticipated this collapse. And so every time you spoke to him, we would be talking about this and that, and he'd bring into the conversation, he'd say, "Oh, well, the economy is going to collapse." And, that was true. The economy was going to collapse. And so, in a sense, his statement was correct, but it wasn't informative. And the reason it wasn't informative is because we knew before he opened his mouth what he was going to say. That's what made him boring. But in an information theory, from an information theory point of view, it's what made his statement uninformative. Despite it being correct, it was useless because we could predict it. And so, again, we have this idea that the predictability of a quantity reduces its information content. So again, here we go. We have the economy, the intrinsic state of the economy, the future of the economy. You have me, you have Stefan in between, and this is a poor communication channel because Stefan always says the same thing. So what is information theory? Well, the theory of information is an attempt to allow us to quantify the informativeness of information, not its salience or validity. It's not whether Stefan was correct or not, or whether it was important. Obviously, it was important whether the economy would collapse because it affected our economic decisions. But what it can assess is how informative Stefan's statement was based on how predictable it was. And in his case, it was completely predictable and therefore not informative. Okay? And so here we have Shannon's formula. So this formula was discovered, I guess, by Claude Shannon, coming out of his work and his thinking about radio communication, codes and so on during the time of the Second World War. He worked in Bell Labs and published 2 papers on information theory in the years immediately after the war, and these are amazing papers. He didn't just introduce information theory, but he just did a lot of it. They contain so much. He managed to push the theory incredibly far. But this is the basic quantity. It's what's called Shannon's entropy, H of X. It's related in some ways to the entropy in physics, quite how or in what detail that relationship works is complicated and controversial. He was advised to call it entropy on the grounds that nobody understood what entropy was, and so he could say whatever he liked. Anyway, you imagine that you have a random variable x, and there's some outcomes associated with x, x1, x2, all the way up to xn. So we're looking at the discrete case now. The differential case, the case with continued random variables, is actually quite complicated, and the relationship between the discrete and continuous case, although fully tractable, is nonetheless a little bit confusing. So we're going to deal here with the discrete case. You have n discrete outcomes, x1 to xn. Now in blue, belonging to the set of outcomes, and each outcome has associated with it a probability px of xi. And then the formula for Shannon's entropy is minus the sum over all the possible outcomes of the probability of the outcome by the log of the probability of the outcome. So I'm going to talk more about this formula in the next lecture, describe some of its properties, explain why, give some justifications to why we think, or why Shannon proposed it was a good quantity to quantify the information content of a signal. But for now, let's just calculate it in the case that we dealt with in this lecture. And so in the case of the Netflix star rating, 1 star has 0.016, 2 stars 0.310, etc. There are 4 possible outcomes: 1 star, 2 star, 3 star, and 4 star. So if we work out the probability of 1 star multiplied by the log of the probability of 1 star, so that's minus 0.016 by the log of 0.016, and then for 2 stars minus 0.31, the log of 0.31, etc. That should give us Shannon's entropy. I'm taking the logs to the base 2. Of course, changing base is just a matter of dividing by the log to the base 2, or whatever you want the new base to be. Because we're dealing with information, it's logical and useful to measure information in bits, and so these are logs to the base 2. But in other circumstances, you might use a different base. As I said, just a multiplicative factor away. That, anyway, 1.28 is the Shannon's entropy for this channel. The channel being the star rating of the Netflix films. What would happen if all the stars had been equally likely? Well, that's obviously a superior ranking system, because the problem I described with the Netflix star ratings is that very often you're told that a film is in the same sort of category of starredness as 0.62 of the films. And as such, the outcome of looking at the number of stars the film has is not typically unexpected. Here, we make the predictability of the outcome of that experiment, looking how many stars a film has, as unpredictable as possible by imagining that we've changed the star system so that each of 1, 2, 3, and 4 stars is equally likely. We could do that by just changing how we histogram the data, basically. And in that case, the terms, the p of xi log 2 of p of xi, well, we just get 4 of them the same. Each of them looks like 0.25 by the log of 0.25, and it's easy enough to see that that gives you 2, because the log of a quarter is minus 2, and 4 times 0.25 is 1. So in that case, the more informative case, then Shannon's entropy has given us a larger value, which is kind of what we want. What about the Stefan-like case? Imagine that whenever you looked at the star rating of a film, it was always 1 star. Well, then you get the log to the base 2 of 1. There's a delicacy, which is in this formula, you have to decide what happens if p of x is 0, because 0 log to the base 2 of 0 is not defined. But if you do a limit, the limit as epsilon goes to 0 of epsilon log epsilon, you get 0 perfectly well. So it's a convention in the formula for Shannon's entropy that 0 log 0 is 0, yes. But the log to the base 2 of 1 is also 0. And so in this case here, where before you look to see how many stars a film has, you know it's going to have 1 star, it's useless to look for the number of stars. That's the whole point of what I've just been saying. And in that case, h of x is 0. And so in this example, we have the deterministic case where you already know h of x is 0, the actual case where h of x is 1.28, and then the completely random case where h of x is 2. And so the communication channel we've been discussing, we've looked at 3 possible cases: a sort of very bad channel that contains no information and is unlikely to tell you anything about films; a very good case where before you look to see the star rating the film has, you have no idea what the value is going to be, no idea whatsoever. That has a h of x as 2. And then the intermediate case, which is actually the case of the average star rating of films, which gives you 1.28. And as I said, that's not quite even in the case where you're getting h of x is equal to 2. It could just be that the way that Netflix works out the star rating is it flips a coin each time and gives you flips 2 coins and gives you 1, 2, 3, or 4 stars accordingly. That would be useless information, but it is something that you wouldn't have predicted before you looked. And so as far as Shannon's entropy is concerned, that would be the most informative case, even though it's not guaranteed to be the case that's maximally informative about the actual quality of films. And as I said before, there are information theory quantities for assessing that. But for now, that's a motivation for Shannon's entropy. We'll continue talking about Shannon's entropy in lecture 2. Thank you.